So Don, are you there? Hello,
I
Don.
am here.
All
I
right,
am
you're on.
here. Can you hear me? Can
Yes,
you hear me okay?
you're perfect.
Okay, Demitri. So I want to just introduce what we're doing here. So Demitri and I have been working on the Core 1, which is an FPGA fourth, and we tried to use very high-level behavioral system Verilog code, and Demitri is going to show you that actual code. It's up on GitHub. I have started designing an actual development board that's gonna. I gave a talk last year about a fourth supercomputer idea, and that is coming to fruition for next year. And we're going to have basically a fourth computer tablet that will be running 32-bit fourth, and also it could run up to 8 to 10 32-bit Core 1 computers, and probably running about 200 fourth instructions, 200 million fourth instructions per second for each one of those cores that are running. So Demitri, you want to take it over? You there?
Yeah, sure. I will take over, and I will go through the code as I have it now. It's actually been a few months since I've come back to the Core 1, since I've been working on things in my personal life. But I will show you what I've got and what we're trying to achieve. So I will just share. I'll stop my video just in case I run into any bandwidth issues. And here is my. So just confirming that you can all see my notepad file. Good. Okay. So we begin with our parameters. We try to make whatever we can parameterizable in the Core 1. Also, it gives you a name to your number, so you have a bit of documentation for numbers, which really helps. These here are our opcodes, which we actually define using an enum. So it's actually very easy to add new opcodes if you need to, because you will just add them at the end here. This makes it great if you want to add new functionality to the Core 1. And initially, we weren't sure exactly what we would need because we were considering a number of different applications, including AI. Now, with that kind of environment, we wanted to set it up so that you can add whatever functionality you need. And it all kind of begins here with this data type of enums. Again, it also makes things readable because you can see the name of each operation. These are more parameters. This is the I/O. So we've got, I think this transmit and receive is for an RS-232 UART connection. We've got LEDs, we've got some PWM channels. These are Don's favorite for being able to drive motors for robotics. And we actually have SPI as well to communicate with other cores. We've got some internal memory. Number of different registers. Okay, I'll stop here because this one line is actually quite significant. So here we actually have our stacks, so data stack and return stack, both of which are circular stacks. The implementation of which is incredibly simple. Basically, what we do is we have the stack and we make sure that the width of the pointer is a power of 2, so it naturally wraps around once you overflow. So we don't have to deal with stack overflow and underflow errors. We just use a circular stack, we think. I think we got this idea from Chuck, actually, so thank you very much for that idea, because this simplifies our stuff a lot. We've also got our boot ROM, which I will show you in a moment, that contains codes that we execute on startup and a little bit that we execute otherwise. So the rest of this is pretty much just various registers. We just define them at the top and we use them later on, which I actually think is quite Forth-like, because one of the main things I think in Forth is actually that you have to define things before you use them. So let's begin with our boot ROM here. What is this? This essentially contains a combination of a sort of interpreter and code that has been defined in a dictionary. Now, our interpreter is this execute. That's it. So we have this one word execute that takes addresses and keeps jumping to those addresses and executing the code there. So that's a one-liner. And the rest of this is for other instructions. Now, here you can actually do some microcoding, because some things you might not want to actually implement in system Verilog. Some things you might, some things you might not. But if you think it's best not, because you have limitations in the number of LUTs available, you can also write it in here as microcode. And we've discussed some ideas earlier. For example, division seems to take quite a lot of fabric for an operation that's probably not going to be used too often. So we've considered actually adding it here instead. And if you really wanted, this could be it. All the code that you ever want to run and execute could be here. You could do without most of the rest of this, but we want to go beyond that level and have a computer that we can interact with. So let's go on to see how that's done. So here we have the dictionary structure. I've defined a few words in here. It actually took me a while to get around to this point, but I'm quite pleased to have it. The structure at the moment is very, very simple. It may change in the future as we add more functionality. But basically what we have here is the first field is where the next entry is. Then you have the name of the word itself. This right here tells you how many cells it takes up. So the name red, which tells on the red LED, only takes one cell. And then after this, we have the boot ROM address containing the codes that we're going to execute. So this is sort of equivalent to an execution token, or CFA. Now, in this talk, I might kind of use them interchangeably because they more or less work out to the same thing in our implementation, but we are having more discussions on this too. So if I say execution token, sometimes I probably mean CFA, and if I say CFA and that doesn't make sense to you, then I probably mean execution token. So this is our dictionary here. I have a few words defined. One thing I'm quite proud of is you now have the whole words in there, whereas before I think we only use one cell, but now we're using a multi-cell technique. And this is probably one of the main pieces now that we'll look at, the outer interpreter. So how have we done this? First of all, we have a reset state, and that's really handy because if something goes wrong, we have a bug and you get stuck, we can just reset and go again. We start off in the idle state. So we wait for the user to type in anything. Once they've typed a command, once they've typed one character, we then parse it to decide what to do next. So we go to state parse. Now we ignore the first two here, and we'll come back to them later because these are for white space, and I do something special when I receive a white space in my implementation here. But otherwise, if you receive a character and it's say it's a number or it's a letter, we load it into a buffer called word in. And what we actually do is we immediately start looking up in a dictionary. Now, this might surprise some people. Why would we start looking as soon as we get the character? The thing is, this comes from a time when I was implementing the Core 1, when words were only one character long, and a really early version. But actually, I figured even if you have multiple characters, the dictionary lookup is so fast that by the time the UARTs module is going to process the next character, it would have finished searching the dictionary. So, I mean, this is true unless your dictionary is absolutely huge, which we probably wouldn't do for this core anyway. So we begin looking it up, and the idea is that by the time you finish typing the word, you would have already found it in a dictionary. So that actually saves some time. So the way we look it up, it's quite simple. I will kind of gloss over some details here just to keep it high level, although we've tried to make things readable where we can. First thing we do is we get the link address, so we know where the next entry is. That's the first part of our dictionary layout. We then search for whatever word we've parsed so far. And to summarize this here, if we find it in the dictionary, like if we compare all the characters and they all match, then we will get the execution token, which is another state here. And let me see, we basically do that by just reading it, because that's stored in the dictionary. If not, we follow the traditional fourth method and we then check if it's a number. And that, of course, some people have asked, oh, why do this? Why check for a number only after looking through the whole dictionary? Why not just identify the number first off? Maybe that's a question Chuck could give a better answer to, but to me, I like this method because it allows you to turn anything you like into a word, even a number. And maybe in some rare applications, when you type in a number, you want that number to behave differently. So you have the ability to overwrite anything you like. Furthermore, it just simplifies the parsing anyway. So here is number. A number needs a little bit more work at this point in time. For the calculations we're doing just 1 byte, but we will soon extend it to work on numbers of any length. And we do a very simple conversion here because, and this is the thing we like about System Verilog, we can just type this to represent ASCII 0, and we just say we subtract that from whatever byte we read in. So that's how easy the conversion is. Of course, there's a little bit more code to be added, but this is the core of it. And again, pretty straightforward. You subtract ASCII 0 and you get whichever number. If you received an ASCII 1, you subtract ASCII 0. Well, the difference between them is 1 because the ASCII numbers are in order in the ASCII table. If it's not a number, then what we do is we add the CFA for words not found. So we have a kind of error in the boot ROM. This is the boot ROM address. So I'll just scroll up to it really quickly. Sorry, wrong place here. And what we do is again, you can actually type question mark so you can see what you're outputting, and we just emit that. So it's not a lot, but it's something, and it takes up only a small amount of fabric. As for this part, of course, if we do actually identify the number, we compile the CFA for an operation that we call number, which pretty much all it does is it takes the value out of this FIFO here and puts it on the stack. So each time we get a number, we store it away in a FIFO, and I'll come back to why we do that in a moment. So now that I've shown these main states, let's kind of imagine a sequence, right? Let's say I'm typing in red, R-E-D. Okay, what happens with a state machine? Well, we receive the R. We'll go to the state called parse. We'll put it in the buffer. We'll go back to I. We'll try to look that up, but we'll fail because there's nothing called R in the dictionary. But point is, we do R-E-D. By the time we finish typing it, we will have looked it up in the dictionary and we'll know the CFA. Then what happens? Well, what we actually do in our fourth here is the next thing we usually is likely to type is space or return, new line. Now this bit I quite like, because let's say we do space, right? There's some similarity between the way both of them are processed, but say we put in a space. What we actually do is take this execution token, or CFA, and we essentially compile it. We put it in a queue to be executed later. So that just sits there in this queue, and we reset some variables here that were used while we're going through the state machine, because at that point we've completed a whole operation. We don't need to remember anything now. We can just wait for the next word to be typed. Interestingly, the equivalent of no-op in our I would say the equivalent of no-op in the context of the outer interpreter for us is actually execute. And the reason is because execute waits until something is available to execute. So it's blocking. It's not something that expects a value on the stack. So if you execute, then we just wait for something to execute. So it just cycles on itself. One thing I will point out here is my use of these kinds of assignments. We call them blocking assignments. The good thing about them is that the synthesis tool should only insert registers where they're needed, and instead it will try to use as much logic as possible to propagate the signals. So that's good because we can run at speed of silicon, rather than being slowed down by registers at each stage. So I've tended to prefer this kind of assignment, but there are some places where I use the non-blocking assignment, but usually when I need to know that the signal will change on the next clock cycle. So some things are very timing specific, so I don't use that, but when we're not concerned, we don't bother. Another case as well is when things need to be assigned at the same time. We also want to use non-blocking, otherwise this would be done sequentially. So we don't really care. If hypothetically, if we can assign all of these things at once, we want that. And that's something that the FPGA is actually capable of doing. So I think I've gone through everything here except execute. When we receive a new line, the difference between space and new line is that the state we go to afterwards is the execute state. And what we do is, if the FIFO is not empty, then essentially nothing. We just say that there's execution tokens to execute, so xt valid. So that will stay high while there's still something to execute. So in other words, when you type one line of fourth for the core one, we actually compile each word and then only execute, and then execute those once we hit return. We don't take the line as a string and then process it afterwards, and look up each word one at a time and execute them one at a time. We do all of that before. So very, very, very speedy. And I believe at the moment we're running at 12 megahertz, but we're looking to plot that up to 200 megahertz in the future. So we'll have a super fast dictionary search. Compile is still to be implemented. I was looking to do that before I had to take a bit of a break from this project, but in principle, it should be quite easy to implement compilation based on the fact that we pretty much compile as we go along anyway. The part that is sort of challenging us is, one, expanding the dictionary, just because that required a little bit of logic. And two, we are sort of a token-based forth, but if the user has some words that they define, those will need to be CFAs, and we're wondering how we can distinguish between the two. So that's something that if any of you have some comments after this, that would help us if you have any ideas on how we could solve this. Right, I'll move on to the rest. So this is the outer interpreter, which I've implemented in Silicon. We'll skip over these for now, these bits of code. And I'm actually going to show you the main loop. And we called this the inner interpreter originally. So first of all, look how simple this is. This is actually the main loop in our program. Right, the main, not even a program, this is the main loop of our processor. Now, I think this is actually quite forth-like in the sense that we have used tasks, something called tasks in System Verilog, to hide a lot of the complexity. We've used them in a similar way to how we'd use words. So you can see the structure of what we're doing quite easily. And the basic... Someone unmuted? I'm asking a question. Okay. Yeah, if we're not busy, then we'll fetch opcodes. And if we're not skipping opcodes, we'll execute them. We'll come back to the busy flag, but basically what it is it's a way of halting the fetch so that we can finish executing an instruction, because we allow instructions to be, or opcodes to take multiple cycles. There's also other cases where sometimes you need to skip over something in memory. Maybe, for example, an opcode is followed by some data and you might want to skip over it. You know, that's an option that's available there. So now that I've shown you this main loop, let's go through each of these parts, starting with reset. So these are a task that allows us to separate out our code and isolate them. And so elsewhere we can see clear structure. I won't go too much into this, but in reset, we initialize the boot ROM. We also initialize the dictionary, and we reset all of our pointers. As well as flags. Busy and skip up and UART send are all flags in this system. This is where we fetch our opcodes. Again, very straightforward logic. I mean, the else condition, which is normal execution, is we read from the boot ROM and we increment the pointer. So, I mean, that's pretty straightforward. Any C programmer would understand what this is doing. When we need to branch, it's also quite straightforward, because we basically just use the branch address to index into the boot ROM, and then we do some kind of updating of pointers and flags afterwards. Very, very simple fetch. With regards to execute, it's longer, but this is where we have to actually define all of our opcodes. So we extract that from our data bus here. But one thing I will mention is that we are looking to add a memory manager, though, because we don't just want to be able to fetch from the boot ROM. We'd like to execute code in maybe external RAMs as well, or other internal RAMs. So I think in due time we'll add logic so we can fetch code from other sources. But you know, this shows you the idea of what we're trying to do and the basic structure. I won't go through how every opcode works. It's not helpful here. You can look over it yourself. But what I might show you here is how we implemented our own custom opcode, IO LED. Now, I don't know any for CPU where someone would make an opcode just to turn on LEDs, but we did because it was a way of seeing that Core 1 was alive. And it was so simple to add because you just, if you remember at the top of the file, I defined all the names of the opcodes. Use it down here in this case statement, write whatever logic you need, and that's about it. Of course, there's other bits of logic in this file that do the actual driving of the LEDs, but our idea is that it should be quite simple to add new things and then interact with them as we please. We also have one called IO button, but we have no buttons on our board, so I think this is maybe a legacy thing, but it shows you an idea of how simple that would be. Words like emit. Emit's an interesting one because that does take multiple cycles, because I believe emit waits until the character has been set over UART, or the UART might be busy, so it might not be able to send it straight away. So this is a multiple cycle operation. And this is where we use the busy flag, because what the busy flag will just do is it will halt fetching until this is completed. The good thing is, because we use the blocking assignment, as soon as the operation has finished to the nearest clock cycle, we will continue executing again. So that's the nice thing. But this is powerful because, you know, some operations you want to add, some new opcodes might take, I don't know, hundreds of cycles to complete, could do something quite advanced. That doesn't matter in the Core 1. You have the ability to add those. Of course, most of these execute in one clock cycle anyway. And here's the actual execute opcode. As I say, it waits until there's execution tokens or CFAs. And when there are, it just keeps branching to them and executing them. So this opcode actually does quite a lot in our system. It's pretty much the heart of it, and that's why it's the first instruction in the boot ROM. Of course, here we have number, which, because of the previous processing, all it has to do is take the number out of a FIFO when it's ready. Now, the reason we put numbers in FIFO is because of the same thing I said about, we sort of try to compile things first and then we execute. We don't go along one at a time and look things up. We try and compile them all first. So if you come across a number, it's not a case of, okay, we're going to process this number and do some stuff, put it on the stack, then we're going to do the next word and run it. No, we actually need to store the number away until we're ready. So we just put it inside this queue and we can put it out when we need it. Any other significant bits to show you? I will briefly show you what we have to communicate with the outside world, but I'm not going to explain this. So UART receiver, I wrote this myself. Transmitter, also did this. And then we have SPI that Don added to communicate with other Core 1s. That is a future thing, really. I've not tried connecting up the Core 1s yet, but actually it's quite interesting because I in the previous presentation about SVFIG, I heard Core 0 and Core 1 mentioned and how they communicate with each other, and it made me laugh because essentially we talk about Core 1s communicating with each other because we called this project the Core 1. But yes, you can have Core 0 and Core 1 communicating, where 1 is the main one, which will have this UART and stuff and communicate with the outside world through the outer interpreter. Maybe another one that's more of just a slave that might just run microcode instead. So it'll be much smaller, which means that you can fit more of them on your FPGA. And you can take advantage of having these multiple core ones running at the same time. And here's just something we added for ourselves, just fourth 83 word set, just to give us an idea of what fourth usually contains. And I have reached the end here. So I think I'll hand over to Don and just ask Don if if there's anything he would like me to mention in this before I fully hand over to him.
Yeah, so inside of the FPGA, you're going to have like a full fourth engine, and this is the code for the full fourth engine. But you could have 10, 20, 30 stripped down cores, and they don't need the UART, they don't need the compiling and all that other stuff. It would just use this microcoding like what he's showing right here in the boot ROM, and you could create 32-bit cores that are less than 2K, 2000 LUTs. If you made them 16-bit, I did a quick synthesis. I just changed the data width from 31 to 15, and I resynthesized it, and we dropped about 30 or 40% of the LUTs being used. So you could make an embedded system. 16-bit machines are perfectly fine for lots of stuff like motor control and things like that. You don't need a full 32-bit. So that would allow you to put more 16-bit processors, and these things would run at 200 megahertz. Core is an acronym for Complex Over Risk Engine. So the busy flag allows us to create very complex opcodes. Back in the 90s, right? We had instead of RISC, we had complex opcodes, and then all of a sudden we decided, hey, we'll have opcodes that do very simple things and execute faster, because you're going to have to that allows you to increase the clock, but it makes a requirement that the opcode has to finish in whatever you made your standard is for your RISC engine, whether it's one clock cycle or two or whatever. So the busy flag allows us you could have a very complex algorithm, make it an opcode that you just call, and then the engine stalls until that complex opcode is finished. And then of course, if it's a one cycle opcode, then it's going to execute at the speed of the clock and speed of the fabric. Also, the blocking, so this shows we're using continuous assignment statements. And what he talked about, this is a parallel action. When use the equal sign in Verilog, it creates combinational logic on the FPGA instead of registered logic. So one of the things that Chuck did on the green arrays was he used combinational logic so that the processing just flows through the fabric at the speed of fabric. It's not waiting, it's not every time the clock changes state. So we're doing the same thing here. It's kind of a hybrid approach where our opcodes are all combinational logic, and will run, even if they do multiple functions, they're running it like a typical FPGA is 2 nanosecond delay, propagation speed, I should say. So it's going to be a very fast machine. Is there any questions on this code before we move on to the hardware? Guess not, huh? Okay. Let's see.
Okay, thank you. I'll stop sharing so I can go over to you. And yeah, if anyone has any questions at the end, feel free to ask them as well.
Yeah, and if anyone has any thoughts on token versus CFA, we've had a couple ideas. I had was because opcodes are enums, they start at 1. You could say we'll never have more than 1,000 opcodes. So if we fetch the execution token out of memory and it's less than 1,000, it's obviously a token, and then our current code would execute it. If it's greater than 1,000, that could be external memory, and then it could treat it as a CFA, and then look for user colon definitions, that sort of thing. So that's one idea. Another one would be, you could just in the boot ROM, you could say you could put a table basically with the opcodes in it, but then you'd have to fetch it and then execute the token because we're token based. So those are two thoughts that we had. If you guys have some ideas, please let us know. Let's see. So my part of the presentation is going to be really tiny. Can you see my screen?
Yes.
Okay. So we did start a Facebook page. We call it AI and Robotics because it's going to be more than just Forth. We're going to be talking about AI and robotics on there, and there I will have a link. I'll put it in the chat when I finish the conversation, the presentation. So this is the full Forth supercomputer tablet idea, and I've already bought about $1,500 worth of parts already. I've already bought all the FPGAs. They're 24,000 LUT FPGAs. Our Forth engine, our full Forth engine with interpreter, compiler, and RS-232 goes in and it executes, including 32-bit division, which is really expensive. It's like almost 500 LUTs just for division. I hate it, but maybe some of you guys have some ideas on a better way of doing division. I would, as an embedded guy, I very rarely use division, except for maybe converting a number to display it to the user. So so anyway, we're going to have an LED screen, and this is going to be a 7-inch diagonal screen. It's going to be 800 by 480, 24-bit. It's color, so it's going to be RGB 8-bit color, and I've done this before and it worked out super well. So I take an SRAM and that becomes the frame buffer, and so all you do is you scan through the addresses at the video pixel rate, and then whatever's in the memory just shows up on the screen, and then your computer just updates memory, the memory locations for our, it's going to be, this is a 32-bit memory, so it's 24-bit color. And so you just update, you can load an image in here and it would just display it. You could do it in a 60th of a second. You can completely replace this memory. So you probably wouldn't even see it blink. So that's the display. And then we have the serial interface. We will have I'll put a USB hub in here, so you can put a keyboard on there. Gonna put Brad's ESP32. Brad, I finally figured out how to put this darn thing and have all the interface circuitry, so it works great. So we'll put Brad's Forth in here. That will give you a Wi-Fi and Bluetooth. So DDR4 memory, you get a lot more memory, but it's the problem with DDR memory is it's page based. So typically it's like 4K is the page size. If you don't get a hit within the 4K, then it's going to cost you 125 nanoseconds to go to a different page. So let's just say you have a jump and it goes outside the 4K page limit, then you have a 125 nanosecond penalty. If it's within the page, you can access the data at 25 nanoseconds, for example. I'm going to also add cache RAM. So this RAM chip is designed to be used as cache on a motherboard, and it's a 32-bit. It can run at 200 megahertz. So it can basically run at the speed of silicon. So we're going to have our main core, which is doing our full fourth computer, which has compiling, interpreter, and all that stuff, will be on this one. And then this will be a fast core. So this will probably be like about 40 million fourth instructions per second computer. This will be 200 million, this guy here. It'll be less memory, be 256K by 32 bits static RAM. So you already have two cores. You have a super fast core for doing super fast operations. I'm going to put audio in there, and I'm going to put some nice speakers. They go from about 400 hertz to 10 kilohertz. They'll be stereo, and we'll have audio amplifiers on those. We'll have dual microphones because I want to experiment with like using localizing sound. So then that'll go into a mic, and these guys will be, custom coded Verilog to operate those subsystems. They'll be operating in parallel to the main fourth engine. So the fourth engine isn't going to have to do anything but, put out what the tone is, for example. And then you can have, 8 to 12 micro-coded fourth cores, and they'll be running at the speed of Fabric. They'll be running at 200 megahertz. They'll only have the execution token and the bootloader type code that from Dimitri's presentation in there, and you just microcode them. And of course, the microcode is fourth instruction, so you're writing it in fourth. So that's the main computer. The board will fit on the back of the LED screen. So we're basically making a tablet here. So what I want to do here, the goal is provide hardware to support the Core 1 development. I want to put some I/O and some interesting things on the board so we have something to program, like the screen. We could build a full GUI in this thing. When I did this that display, when I did this display this way for another company, they created a complete GUI for a SPOC controller. They asked me, how to do this, and first idea was use SRAM, and it worked fantastic. It was great. So they created a complete GUI. It looks like Windows. It'd be open source, open hardware. We get done. I'm doing all the hardware design in KiCad, which is free, open, free to download. I find it, if you've ever played with or used Eagle, it's actually better than Eagle. They got some features in KiCad that's is like a more higher level schematic capture board layout. It's damn good. I really liking it. I'm still on the learning curve, but not much of a learning curve if you've ever used OrCAD or any of these others. The other thing was, as you know, I've done some work in solar power and created my own solar panel. So I've been using these back contact solar cells, and we can actually put solar cells on the bottom of the computer when you're not using it. Just flip it over so the solar cells are exposed to the ambient light, and it would power itself. It would recharge the batteries. We want to be able to experiment with novel computer architectures, and so this is, we're going to be able to do that. Fourth will be the central processor, but we could create other custom processors, AI engines, neural networks, that sort of thing. There'll be a platform for advanced robotics and AI research. That's really you know, where I want to go. When I retire, I want to be doing that kind of stuff. Hopefully I can retire next year. I don't know. Here's Chao Chang is also in our group, and he's been you know, he was very close to Dr. Ting. They were working on some pretty amazing stuff. The guy's fantastic. He's over in Taiwan, I think it is, and he's been doing a lot of work with neural networks on NVIDIA, and he's also an FPGA guy, and so he sees that the work he's doing on neural networks can actually be incorporated in a Core 1 computer. So this would be a version for him where he needs 8 cores running simultaneously to do his neural network stuff. And then, of course, this is the main computer core. And then he's got this core here, and that he could use for some very intensive, where he needs some serious RAM, you know, to do an algorithm. These cores will use internal fabric SRAM, so they're going to be limited. They might be a few K by 32 bits in size. So they're kind of like the F18, you know, the GA thing, where, you know, they're going to be limited amount of memory available. So this is kind of a side view of it. So we'll have the LCD screen. I got some nice speakers. They should sound really good. And then here's the printed circuit board that's going to have the main computer stuff on it. I'm going to have 7-inch diagonal worth of PCB. I can fit a ton of circuitry, way more than I'm putting on there. So this board, I'll probably make it full size, but it'll have a lot of area for chips. And in the future, if we wanted to make a custom board and add a lot more chips to it, we could do that. And then here is the user IO board will snap on the back. So let's say we want to do a robot control board. This board, of course, is the, you know, more sophisticated board, and you just mass produce those, and then you snap on a user board for whatever you're trying to do. And you can put you could even put more co-processing on it. You could duplicate this board if you wanted, but, you know, typically what I was thinking is that this is the board that you customize for whatever application you have. Okay, so the very last thing here, let me get out of here. Oh yeah, so here's the group. I'll put the link in the okay, I want to go over the schematic. A few more minutes, I'll be done. So let's see. So this, Brad, this is the circuit that works. This is ESP32. I added a, remember one of the things we had was a problem with the flash coming up too soon. So I added a power on reset circuit. So it has a 100 millisecond delay. It holds enable low for 100 milliseconds to allow the flash to come up and get stabilized before the CPU starts trying to talk to the flash. We were having problems with that when we first started working on the ESP32 fourth in the early days. But anyway, all of this stuff works. This is all proven. I'm bringing the IOs out to a connector here. And this, let's see, how do I get over there? Oh, here we go. Get out of the way. So this is essentially 2 computers in one. You got the ESP32, and then this one here is going to be the core one, the FPGA circuit. So this has got a small FPGA in there, but I'm replacing this with a large FPGA. And this is on the tiny AI board that we're using for development. This is an open hardware circuit. I'm starting with something that works. I'm just going to replace the FPGA and pretty much ship it. It's everything else is good and works fine. So you have two independent computers in the system. So that's pretty much it. Is there any questions? Where do I stop sharing? Hello. Oh, there it is.
All right.
Stop
So speak up, John.
Okay, how much would one of these tablets cost?
Did you hear the question, Don?
Yeah, I did. So it depends whether you want the LCD screen or not. If you just want to, get it and work with it, it's going to be probably $80 to $100, and then maybe another 40 or 50 with the screen and the touch screen. That's I'm just going to add like $20 over what the cost is, just kind of pay for shipping and handling and me ordering boards and all that stuff. It will be open hardware. You could make your own. You can go into business and compete with me. But what we really want to do, Demitri and I want to do, is we want to get people using Vorth. So what better way to do that is just make everything open hardware, open source. And when they start, writing software, and we have some AI applications and we have some robotics applications. I'm hoping that people will take it and then, use it as development to develop their own products, and this could really get Vorth cranking again. Like I was saying to Greg, you need that killer app. Well, if you have a computer that blows the doors off your laptop you paid $1,000 for, and you have to learn a new language and it costs, $150, you're going to learn that new language, aren't you? If we try to compete with C, on its turf, with all the open source out there, Vorth will never do that. We have to show them a new way of thinking, a new way of using computers. And that's what we're hoping to do. So big goals. We'll see how, that you guys are going to have to get involved in this thing next year. When we prove it, we have hardware and everything's working. If we want to promote Vorth and we start creating applications and design your own IO board to do something. And that's when we'll get people interested in Vorth.
Oh.
Cool.
Any other questions from the Zoom audience? Okay, Don, thank you so much.
That was fun. Thank you.
You got it.
I think that there was some mention of demos that weren't performed. If you want to talk
Yeah,
to me
Demitri.
about doing that next month, we'd be pleased to
Okay.
discuss it. We don't
Yeah,
have.
Demitri has a demo. Okay.
All right, Bob Armstrong, are you?
I am.
Okay, it's your turn.
Okay.